Okay, good morning, everyone. The ngVLA, and the SKA will be two mega astonishing new facilities for astronomy with an immense range of capabilities, as we have seen yesterday and today, and we'll probably see also in the week, during the rest of the week. They both will have opportunities to do very long baseline interferometry. And at the outset, I want to make a comment on impact that we talked about yesterday. Before I came here, I spent, just a few days ago, I spent a few days at the ALMA site at 5,100 meters altitude, could see the ALMA observatory and also participate in the VLBI observations that we were doing with the Event Horizon telescope at our APEX telescope, just 2 kilometers away from ALMA, and had some first-hand experience on touching the equipment that we were actually using. I think one of the impacts of the large facilities will be that in the future, these kinds of situations will be difficult, if not impossible, for the normal scientists, especially the starting scientists, to experience. I think it is, however, incredibly important that we understand, that we touch, that we feel our equipment, even if it is in remote places. I had a fantastic time there, almost as good as I have at this meeting. What I will be talking about today, and there's a view at the night sky that you get if you actually stay at the telescope. What I will talk about is millimeter VLBI observations that we do with ALMA, with APEX, and hopefully we'll also do with especially the ngVLA in the future. For perspective, let's remember that we only know for about 100 years that what we look at the night sky, what we see at the night sky, and what we see with the best available telescopes are galaxies in the distant universe. That and the subsequent discoveries, the work over many decades that radio astronomy in particular led in the sort of 60s, 70s of the last century to the realization that the distant quasars that had been found in the 60s and active galaxies in particular were subject in their existence, their creation, and their properties to the black hole paradigm. The notion that the centers of these objects exist supermassive black holes surrounded by accretion disks that dominate the properties of these objects. One of the impetus of a key impetus of millimeter VLBI observations was to ultimately achieve the possibility of making an image of a black hole. And at this point, I remember that I forgot to credit at the beginning, everything I say here today is the work of collaborations around the world, especially around the Global Millimeter VLBI Array and the Event Horizon Telescope collaboration. Now, what you might see was predicted already as early as the 80s, late 70s, 80s, by various scientists, especially, or in particular, Jean-Pierre Luminet. You expect to see from a supermassive black hole, if you have a chance to look at it, a signature dark area that we call the shadow or the silhouette of the black hole, and light around it that is related to the light, to the emission from the accretion disks, asymmetry because we have Doppler effect at play. And the notion, it was very clear that the light that we would be seeing would be a twisted concoction of light from the front of the accretion disk and also from the backside of the object. For about, well, since the pioneering work in very long base interferometry in the 60s and 70s, the quest was on to extend the capabilities to millimeter wavelengths. Today, we have the global millimeter VLBI array operating at a wavelength of 3 millimeters, involving centimeter/millimeter telescopes around the world, an increasing number, and operating on a session basis several times a year. Separate from that, the VLBA, the only really dedicated VLBI array, full-time operational, that however participates in such observations with us, and where I see the hook for the future that the ngVLA in its long baseline configurations, perhaps partly phased, will also be a participant in these things. The development of the pushing of the VLBI technology to the capabilities to be able to image black holes took 30+ years. It started from humble beginnings at 7 millimeters on single and 3 baseline setups, and eventually made its way up to the shortest, currently shortest possible imaging wavelength of 1 millimeter, with experimental work being done at 0.8 millimeters and with aspirations to even shorter wavelengths. The Event Horizon Telescope came together in 2015, operated on 1 millimeter, and at that wavelength we couldn't employ the telescopes that you have seen earlier from centimeter, millimeter, etc. around the world. At the time, 8 best telescopes around the world for millimeter, submillimeter work came together, formed a network that observed in 2017 and led to these iconic images. The supermassive black holes, we believe, in the centers of M87 and the galactic center in our own galaxy. I prefer to show this image that gives you a sense for the scale. On scales of the solar system, you have in the case of M87 a central mass to the tune of 6 billion and change solar masses at a distance of 55 million light years, whereas you have in Sagittarius A star 27,000 light years, a mass of 4.3, more or less very precise, million solar masses. It is the latter that makes Sagittarius A star, our galaxy, so much more valuable from a scientific perspective, because we know from the stellar motion work of the Nobel Prize-winning teams around Andrea Ghez and Reinhard Genzel, very precisely the distance and the mass of this system. They could be fed into the interpretation of the image of Sag A star and led to the highly conclusive notion that indeed we have a supermassive black hole of that mass in the center of our galaxy. It is this work that really highlights that we are, for our small niche of science, that we're in a golden age. We do gravitational waves. We measure the notions from the signatures from black holes, but in particular the infrared stellar motion and interferometry work that is possible with the large optical telescopes and the VLBI work together complement each other greatly in the quest to, it was mentioned already yesterday, to ultimately deliver tests or perhaps even disprove the validity of Einstein's theory. Back to M87 and 3 millimeters, for many years, VLBI work focused on not the properties of the central object that for all of our observations appeared unresolved, but on the jet structures. And so before we delivered in 2019 the image of M87, the EHT image of M87, the best structures we had came from 3 millimeters, and they showed a well-collimated jet structure with substructure on light months and week resolution. The EHT image delivered light day resolution and was consistent, as I said already, it was consistent with the prediction of the structure that we would expect for a black hole given the sufficient model input. Now, only a week ago, Rosen Liu in Shanghai and an international team published in Nature the latest image at 3 millimeters of M87 done with the global millimeter VLBI array at 3 millimeters. And for the first time, we see at that wavelength not just the signature of the jet, but also the signature of the central region, the beginnings of clarity of the signature, actually also of a ring structure. The ring structure in this case is slightly different from what we saw at 1 millimeters. It's a larger and it's a thicker ring, which is attributed to the fact that we have not just the light from the black hole surroundings, accretion disk surroundings, but also from possibly a wind structure that extends outwards towards the jet. So very exciting that even at the lower wavelength with a larger array that covers the wavelength range that also the ngVLA will cover, is able to study in the field, will be able to study in the future, not just jet structures, but also the very compact structure where we try to understand the origin and the evolution of the jets. Meanwhile, the EHT has delivered a number of other results that I can't all talk about. We are measuring magnetic fields. We are measuring various objects where we don't have enough resolution to look at the event horizon structure, but we can study the jets in particular, for example, here in Sene. On this side, you see a beautiful bifurcation of the jet structure. So a lot of work that can be done at that wavelength, and what to expect next from these developments is that through continuous evolution of, I'd say 3 points there, to continuous evolution of the properties of the existing arrays, both the EHT and the ngVLA, but also through new opportunities, we're able to increase the sensitivity, the imaging quality, and the ability to do time domain to measure the changes of the structures in these objects. The first to do will be M87, and then hopefully, because it's more complicated, also Sagittarius A star, where it is more interesting, as I said. To get that, we are working on bringing new antennas into the current arrays that we have. We work on increasing the recording bandwidth that we have for the VLBI experiments, the receiver qualities, and we also are thinking about two possible steps: a dedicated transformational array that will be made up of many more stations than we currently have available, and the holy grail to do this work with much better imaging quality that we currently can achieve would be to go to space. Two projects for which there are design studies, proposals underway. We'll have to see how they come out. It was mentioned yesterday, we live in not easy times. And so the financial possibilities, certainly in Europe, that's the case. I can only speak for Europe, really are limited. So I predict that for the next few years, we'll continue to do VLBI at these wavelengths in the way we have done. We use existing telescopes, we build networks, organize networks around them. And we hope that, I should stress that in the case of the ngVLA, they are already fully open access, open skies compatible, to use Tony's language. But, and also for the EHT, we hope that increasingly we can offer opportunities for scientists that are not necessarily have to be part of a large international collaboration. I personally am focused on the M2 Finders project that is aligned with these improvement attempts. We're trying to actually tackle the black hole paradigm one more further, even though the structure we see in these objects that are showed confirm the predictions from black hole structures, they're not approved for their existence. And on the other hand, there are alternative models that have very precise predictions on especially the shape and form of the magnetic fields. And so we have selected a number of nearby AGN where we don't study the event horizon structure, but we measure the magnetic field's strength and their structure in the inner, say, 1,000 gravitational radii. From the profiles that we expect to get from that, we'll be able to exclude possibly exclude alternative models to black holes. For that, we have to improve the polarization imaging capabilities. We have to develop new methods to reliably, yes, thank you. Oh, okay, to reliably measure magnetic fields, and we have to work on modeling. As I come to the end here, I want to just, these are the European telescopes that we're using, and one step that I didn't mention earlier that improves the capabilities of measuring weak structures is to actually observe at lower frequencies, at longer wavelengths, 3 millimeters, for example, and transfer the phases of the solution to the shorter wavelengths. It could be 1 millimeter, it could be 0.8 millimeter. We're in the process of testing that method. And I say this because it's important that this method will only work if you can do simultaneous measurements at these different wavelengths. And that's something, for example, at ALMA we currently can't do. However, ALMA remains, the ALMA array was the game changer in our field, both in this field, both for the 1 millimeter EHT observations, but also the 3 millimeter observations. And it is absolutely clear, instruments like the ngVLA, like the SKA, like ALMA, and other big science instruments that we have will be the way towards breakthrough science in the future. The same is true in the infrared optical. Only with the VLT was it possible to take the work of Gensel in particular to the next stage. And will it be possible to test the predictions of relativity to even higher degree than currently possible? So we will see in the future, hopefully, also participation of the ngVLA antennas early on, or when they are in the long baseline modes and converted, depending on Joe's plans in the transition team, we'll see the ngVLA to participate in this, and we'll see great signs in VLBI from the SKA as well. I look forward to these things, and I thank you very much.
Thank you very much, Anton. Can we have a show of hands for questions?
So while you think, I'll show you my final comment on impact.
Excuse me. The capabilities of the telescope, everything you've shared with us is awesome. Is there any way that we are adjusting for all these satellites, or what will be the impact of all these satellites on the proposed work?
Well, this was mentioned yesterday. There's two approaches. One is to insist on the regulatory path and try to keep the RFI signals out of our bands. That's not going to work very successfully. The other is to actively work with the providers to define avoidance zones during critical times of observations.
Thank you.
Oh.
Hi, thank you for the talk. So if you're interested in integrating the longer baseline parts of ngVLA into VLBI observations, is the concept of that sort of treating each of those outposts as a separate station, or having the whole, ngVLA extended baselines be sort of phased together and then used as one station as part of that?
So currently we use for the VLBA, which is going to be sort of the adjacent part of this, we use individual antennas as individuals in the large array. They're very far apart across the continental US. Clusters of them can be phased, and if there are several at one location, those would be phased to synthesize a larger aperture. And telescopes over, we are phasing the ALMA array in this compact array to one thing, and a similar thing could be done with the compact parts, or with compact areas, sub-areas of the ngVLA. I don't envisage that we would try, it's thinkable that we would try to phase a very large transcontinental thing. People have thought about that.
Next question.
What do you anticipate being the fastest response time possible to a target of opportunity for NGEHD?
For a subset of the antennas, a few days. They are all used, all the current antennas that we have are used for other things, so it takes a certain setup time. And for the whole array to come online, that will take weeks currently. We are working towards streamlining that so that all of these telescopes, just like our APEX telescope that I showed at the beginning, are small in room available for equipment. So where we tend to have to go there and put the equipment in as needed and then take it away. That's what we did last week. But within a few days, we can be online with at least a subset, and that will improve and become shorter.
Okay, I just want to say, as CMBS4 gets going and we start to get, or even Simon's Observatory, we're going to start to get millimeter band transients that people are going to follow up probably faster than that. And I know you're resource limited, but if it's possible, I think there is some impetus to push on that.
Yeah. All you need is the equipment and a set of recording media on site, and that can be arranged.
Yeah, okay, great.
We have time for one last question in the back.
Following up on the topic of transients, can you say something about how variability affects the systematics of some of these measurements, particularly for something like Sagittarius Star?
Well, the variability, Sagittarius Star is much smaller than MED7, so its typical variability times are much smaller also, and it took us 3 more years to analyze. Don't see where the question came. Okay, sorry. It took us 3 more years to analyze the imaging because the variability is on time scale shorter than the ideal length of the VLBI imaging of 12 or so hours. So we had to work very hard to compensate for the variability, to try to model the variability and the scattering structure in that case to get to a definitive result.
Let's thank our speaker again.